this
Turkeys really weigh that much?
over here. Yeah, absolutely. And Thanksgiving is coming. Okay, so yesterday we talked about unit rates. We looked at proportional relationships, and we mentioned unit rates, proportional relationships. We went through what a proportional relationship was. We talked about how we found the unit rate. A lot of stuff pulled back from 7th grade. Today we're going to take it a little bit further. We're going to look at...
Mr. Cooper, can you please come to the main office immediately? Mr. Cooper, to the main office, please.
We're going to look at graphs, tables, and equations, and we're going to identify the unit rate in all of them. We're going to, and in 8th grade, a big thing that we do, we go across all 3 types of relationships. So you might bounce from a graph to a table to an equation and then back to an equation. We do a lot of comparisons, so we want to identify some things. So the situation that we're going to work with today, here's our scenario. A website contains hundreds of different recipes. Included with each recipe is a table that gives the approximate cost for different numbers of servings. Find the unit cost for this recipe, then write an equation for finding the cost of X servings. Just by looking at the table, you may already know the unit cost. We're still going to go through it in an orderly fashion so we can break it down. We're going to break it down into all pieces, okay? We can use a graph to represent this relationship. Okay. How do I know by looking at the graph that that's proportional?
It goes straight to
It's a straight line.
Straight line,
Most of the order.
and it goes through the origin. Good, we used that term yesterday, that origin where the coordinate of 0, 0 lies. How did we get these points on the line? Like this point here, and this point here. Where are these from? Like, where did they come from? And the reason I ask that, so often we talk about tables and graphs, but we sometimes don't connect how one is going to the other. They represent the same thing. That table is portrayed on that graph, but where did I get those coordinates, those points? Where did they come from? Anyone see where they could be from? Like this one here, this one here, this one here, this one here. Here we go.
Constant rate.
Okay, so we're talking about a rate, but if I just asked you where did these 4 points come from? Because we haven't yet gotten to the rate of this problem, which we're going to in just a minute.
We took the information from the chart and put it in.
Where?
We put the numbers of servings in the bottom and then the cost itself.
So the number of servings we represented on our x-axis, here as you can see, and then our cost is represented on our y-axis. So how did I put these numbers on my graph?
Oh, but you know that for every 2 servings.
What's the coordinate of this point? 2. So do we see where it came from now? Where my servings are 2, that's my x coordinate, and my value of the cost is my y coordinate. So you can easily transpose anything from a table into a graph just by identifying your x-axis and your y-axis. So we can use an equation as well. We have the table, we have the graph. We're going to write an equation for this situation as well. But before we do that, how much is 1 serving of this recipe?
125.
125. And how do we know that?
I'm dividing $2.50 by 2.
Okay, so if we know that $2.50 is how much it is for 2, we can divide $2.50 divided by 2. On the graph, where would you look for that? If we wanted to identify the unit cost, where on the graph would we look?
Number 1.
Which one?
Number of servings.
We're going to look where the number of servings is 1 on our axis, which is here. And we identify that the point there is when our servings are 1, our cost is $1.25. And we're specifically looking there because we're trying to figure out the cost for just 1 serving. Absolutely. Now, this is the division that Jocelyn was just talking about, and it doesn't matter which coordinate you use. If you did 250 divided by 2, you would get 1.25. If you did 5 divided by 4, or 750 divided by 6, or 10 divided by 8, you'd still get the same unit rate at 1.25. How would we write an equation for this? Now let's talk about the equation in words first. Now we know a few things. We know that our x-axis represents our number of servings and our y-axis represents our cost. So we want to write an equation, and what do we want to represent? How are we going to try to put it together? Ibrahim, what do you think?
Try to find out what y is.
Okay, what y is or what the cost is. Okay, so I'll do it in words first because we can explain it in a sentence and then turn it into math. Okay? So the cost is what? The cost of the servings is what? How would you explain how we
The
find
number
the
of
cost of the servings?
The number of
The number of servings. The number of servings. Okay. And then what? So the cost is the number of servings.
plus
For every one serving, the cost is $1.25.
Okay, so for one serving, the cost is $1.25. So what would I do to the servings to find that total cost if I know that each one is $1.25? Say it again. I can multiply my number of servings by what value?
No, the one we had the units.
Exactly, that cost. So let's put this into math, right? We have it in a sentence pretty much. We know that the cost, how we find it, is by taking the number of servings, and if each one is $1.25, we can multiply. And you can tell me for one serving, $1.25. For two servings, how much? $2.50. For three servings?
Fine.
Nah. For three servings?
for 350. No, wait.
6.25.
70.
For three servings. Now this is tricky, and I got you. I knew I'd get you because you're not just moving to the what's going on in the table. What's three servings isn't there? How much are three servings? If two are $2.50, what do we have to do to go one more serving?
And
Add $1.25. So how much is our third serving? $3.75. So our cost, and in this example, what variable are we representing our cost as? Y. Okay, so Y equals. How are we going to represent the right side of that equation? If we're saying the number of servings times 0.25x. Absolutely. Y is our cost, and it's going to equal $1.25 times the number of servings. So, like we just said, you could have told me one serving, two servings, three servings. If I asked you how much 100 servings would be, you can use that equation, which would probably be a little easier than the graph or the table, to tell me what the cost would be. How can we tell? So now we're going to transition. When you talked about proportional relationships in previous grades, you looked at a graph and you said, two ways I know, straight line through the origin. Let's say you don't have the graph and all you have is the equation. By looking at that equation, how do I know that it's a proportional relationship? Think about the components. If you're looking at a graph, we know two things. We know, what was the first one? If we looked at the graph?
Straight line.
Straight line, okay.
Goes through the
Straight line. And we knew through the origin. Is there any part of that equation that tells me that it's going to be a straight line? And this is really good for those of you who are taking notes down. This is a really good connection to make. What is it about the equation that shows me that it's a straight line? What does a straight line mean? What does that mean, though? Why is it straight and not curved? Jordan.
Because of the 1.25x, like the multiplying is that, like.
Okay, so Jordan's saying that it's straight because of the multiplying. What about it? Because it's not just
Consistent.
multiplying.
You're using that.
You said a word.
Constant.
Consistent, constant. Anyone want to build on that?
You build on it.
That's a constant rate of proportion.
Because it's a constant rate.
That's what I was trying
Yeah, and you were saying because, and you explained it perfectly. You said we're multiplying by 1.25 every time. So it's growing at a constant rate. So what identifies that this is proportional is that it's always going to grow at a constant rate. Things that are not constant this would be an example. That's not constant. Imagine if I put in a 1 there. 1 times itself is 1. But then 2 times itself is 4. So all of a sudden, my growth is going to look like that. It's going to curve. We're going to focus on nonlinear relationships more towards the spring. But right now, just the fact that you're always growing at the same rate shows you that it's a straight line. Now, we've got this one. Constant rate. So it's going to be a straight line. How do we know, though, the second component? Because we have a lot of straight lines that are not proportional. So it's not just that it's straight. The other part is that it goes through the origin. How do I know that that equation goes through the origin? What do you think?
If you can divide it by itself to get 0, I mean,
Now this is something you may never have been asked before. What does it mean for a line to have, what does it mean for a line to go through the origin? And I'm not talking about proportional or not, even if it's a curved line. If a line goes through the origin, what does that mean?
start to 0.
Well, what if it goes off?
It's negative.
So what do we know about that line because it goes through the origin?
Has to do like the X and the Y.
Potentially.
I just don't know what about.
What does it mean for there to be a point on the line? Like a coordinate, right? That line has a coordinate of 0, 0. What does that mean?
That there was once no value.
Say it again.
That there was once no value for it.
For what?
There's, I know the X and the Y.
So add context, and we can use this example. This is where you're gonna get there. But I don't know if you've ever actually had to make the connection between the graph and what it really means. That line represents the website and the recipes and servings and the cost. So what does 0, 0 mean?
Nothing.
For this situation, the X of 0 and the Y of 0 mean what? For 0 servings, you pay $0. And how can I use the equation to prove that?
Well, divide everything by.
No, what word did you just say?
0.
What am I going to do with the 0?
Plug in.
I can plug it in, I can substitute. If I substitute a 0 in here, what is Y? 0. Right? 1.25 times 0 equals 0. That proves that this is on line. Now imagine this. If I plugged in an x of, I'm going to erase this for a minute. If I plugged in an x of 4, if I substituted in an x of 4, what will y be? What's 4 times 1 1/4? 5. That's how I'm getting these coordinates. So when you see the coordinate 4 and 5, if I plug in the x of 4, it will calculate out to a 5, to my y value. So the equation gives us a lot of information. If I just had an equation and I needed to graph it, I can do that pretty easily. How many points do I need to create a line?
2.
2. So if I had an equation, what could I do to find 2 points on the line? I could substitute a number. If x is 0, what's y? If x is 1, what's y? I can create a line from that. But the way I know that this is proportional, the same 2 reasons. First, I know that it's a straight line because it's a constant rate. And second, I know it goes through the origin because if I substitute in a 0 for x, I calculate a 0 for y because 1.25 times 0 is 0. And there will be examples when you'll be asked by looking at an equation if there was a proportional relationship or not. Could I add something to that equation to make it not proportional? What would it mean for my line to be, for my relationship, I should say, to be not proportional or non-proportional?
Maybe you could do like there are equations that we had to solve last year where the equation would be like this, but like for everyone you would have to add like 5 or something.
So this?
Yeah.
Okay, so let's think about this. Is that a straight line if I graphed it? Does it still grow at a constant rate? It still grows at a constant rate because every one time I'm still going to increase 1.25. Is that at 0, 0? No. If I put in a 0 for x, what's y? 5. So this line actually goes here. It goes through that point. That's not proportional. And we're going to work on those types of equations next week. Today we're just focusing on proportional. So let's narrow down the unit rate. We already know it. We talked about it already. But let's recap for the graph. Where do I look in a graph to find my unit rate? Okay, I'm looking for 1. Where? Right there. I love the hand. The other class did it too. Right there. Okay, where is that? Where's there? If I'm trying to find 1 serving,
Right on the right.
where my x-axis, my number of servings is 1, so I can find it. There's my unit rate of 125. How about in the table? Is my unit, so for my graph, you can look where x-axis of 1. How about in my table? Is my unit rate there? How do I get it? Division, okay. I can divide, I can add that value where my number of servings is 1, and if I follow the pattern of my table, every 1 is an increase of what? Every 1 serving is $1.25, so if I'm going from 2 servings to 1 serving, well, from 2 to 1, I go backwards, and that's where I'm getting my 1.25. Where's my unit rate in the equation? Not a trick question. Where's my unit rate?
At the bottom.
Right?
In the equation.
Oh.
We already know the unit rate is 1.25. That's not a secret. Where is it in the equation? Let's use the vocabulary.
Is that the coefficient?
It's the coefficient. Yay. Coefficient. This is in proportional relationships. So if you are taking diligent notes and you wanted to identify in a proportional relationship whether you have a graph, a table, or an equation, this is where you can identify your unit rate. In the equation, your unit rate is that coefficient. It's going to be your constant rate, the rate of growth. In your table, it's going to be where your number of servings is 1. You may have to do a little calculation to find it. It's not always going to be just the first number in your table. And then in the graph, which we identified yesterday, we're looking where that x-axis, because we're finding our number of servings, is 1. And this is key here, because our unit rate, I've been wanting that to go up for quite some time.
What is it?
Oh, the blinds. The blinds
Oh, I
just
thought it
went up.
was squirrels.
No.
I really thought they were going to attack me.
That's okay. So in a proportional relationship, this is where you can identify your unit rate. What's the constant of proportionality? Now, some of you might remember this from last year, but let's think about the word. What does the word constant mean? Consistent. Okay, I see the hands showing like the same thing over and over. And what do you think of when you hear the word proportionality? Proportion. Okay, so we're looking for the consistency of the proportion. So we're looking for the value that keeps our proportion consistent. What is that number in this problem? 1.25. Right? Exactly. That's the value that's keeping this proportion consistent. What else is 1.25?
Unit rate.
The unit rate. So what do you think we could say about the constant of proportionality and the unit rate? They are the same thing. The constant of proportionality is the unit rate.
Why is it called two different things?
So that's a good question, and I can't be 100% quoted on this, but the way I would explain it is that depending on the situation, in a real world scenario like this is a unit cost, right? The cost for 1 serving. But if I just had a generic equation and I was asking you to identify like what's keeping it constant, if there's no context to that equation, then I can't really say it's a unit rate because we may not have a unit to speak of. So in that sense, it would be your constant of proportionality. This is it. I'm recording the lesson, so say hi.
Hi. That's your panic button?
Yeah.
Does it work?
It's not plugged in.
Oh,
So no.
so let's go.
I was going to press it the day it's
You're recording
installed.
lesson?
Yeah, I record them and post them on YouTube. Bye. So that's probably my best explanation. I could look that up if that's something that we wanted to know, but I feel like it's the same representation, but
I
one
agree.
has a context and one doesn't.
I agree.
Or this is just the mathematician's way of making your lives miserable. No, I'm just kidding.
Miss, did you learn all
Don't
this
forget
in
it's on
school
recording.
too?
No, I actually went to school to study business, so I didn't learn like specific math. I have my master's in business.
There you go.
So the slope, we talked a little bit about the slope yesterday. The proper definition that we can use for the slope, and you mentioned it, I'm pointing out Jeremiah because he was talking about like a ski slope. Some of you talked about the slope of hills. The slope is the measure of the steepness of a line, or a section of a line, and it tells us like how fast is our line going up or down. So yesterday we also had identified that when we talk about slope, we say rise over run.
Yeah.
What does that mean? Rise over run? What did that mean?
Like
Like
the
where did it come from?
the y over x.
So, okay, y over x, what is that?
That's the rise over the run.
I see your hands like the up and over.
Right
So
there.
the rise, how would we find the rise?
How much it goes up?
How much we go up? How much
What it go up?
it goes up or down? And then the run would be what?
How much it goes down?
How much? Well, the rise is up and down, so the run must be what?
Where's stating it? Oh, horizontal. And
How much it goes horizontally? Yeah, goes over. And it can be left or right, depending on the line. So, how would we find it on this graph? Where would we find the slope? If I only had the graph, what would you do to find the slope? If you're using the idea of rise over run, that's fine. Go ahead.
Ooh, like with Miss Nieves last year, she would like have us like count how much it went up and stuff like that, and then take that number.
So where do we want to start?
Where the one is like between the 2 points.
This?
And then up.
Okay, so we're going up. How much are we going up here?
1.25.
Okay. And then,
over one. Isn't that one?
so what's our slope? So our slope is 1.25 over 1. Okay, did I have to use those 2 points?
No.
What if I wanted to use the origin and this point? How much do I go up? I went up 2.50 and I went over 2. Okay, which means that the context of that is for every 2 servings, I'm increasing $2.50. So my slope still simplifies to 1.25. So our slope is 1.25. What was the constant of proportionality?
1.25.
1.25. And what was the unit rate?
1.25.
1.25. So we could say in a proportional relationship, what's the same?
The unit rate.
So a proportional relationship. What can we say? We could safely and confidently say that what about, so we have, you said unit rate, what else? Slope, and
Constant of proportionality.
are what?
The same.
The same. Are the same. And that is true for proportional relationships. And when we add the anchor chart to the wall, and I'll show examples, just like what we did today with the table, the graph, and the equation, that in a proportional relationship, your slope is the unit rate. So if you find the unit rate of this, if you find the unit rate of an example, you automatically know the slope. If you find the slope of a line, you automatically know the constant of proportionality if it's proportional. Next week, we'll talk about lines that aren't proportional and how we find the slope. Still the same way that Jordan just showed us how to do it, but when our relationship is proportional, it's a straight line that goes through 0. All 3 of those values are the same. The constant of proportionality, the unit rate, and the slope. Yes?
Are we gonna have a test?
Yes. but not till November.
Oh yeah, what are our test scores?
Oh, I'll give you yours back. We already answered this question, but in the problem, let's wrap it all up. Whether we're talking about the slope, and the slope is really for every one I'm advancing over, right? Every one serving, how much is my line increasing? It's going up 1.25. What does that mean in the context here? The unit rate represents what?
Like
What per serving?
Oh, come.
The cost per serving, absolutely. The unit rate is the cost per serving, the $1.25, okay? And that's represented in the slope because for every one serving, my line is actually growing by 1.25. There's my rise over run. Perfect. We're gonna do a little activity now, and I'm actually gonna pause this. But we are going to represent proportional relationships.